So we're going to start covering thermographic inspection. You'll also see this called infrared thermography or infrared inspection. And what this is, high level, is looking at the heat energy contained in an object in order to perform inspections on it. So thermography has some distinct advantages. It was developed primarily to test and evaluate composite materials. Composite materials are fairly limited in what techniques can be used on them. Right? We can't use magnetic particle. We can't really use liquid penetrant because liquid penetrant soaking into fibers and that kind of thing on composites isn't a good situation. We can't use eddy current testing because most of them are non-metallic. We can use ultrasound, but there's some limits. As I mentioned, it's a non-homogeneous material, and so you get a lot of those acoustic interfaces and weird echoes going on. So though ultrasound is commonly used on composites, it does have its limits. So thermography primarily came about because of the development of composite materials. However, it can be used on metallic structures, and so when you do the lab, you're going to perform infrared thermography on both composite and metallic structures. It has the advantage of being able to detect surface as well as subsurface flaws in a material. It can do a fairly large inspection area, especially if you compare it to something like ultrasonic testing or eddy current testing. And it has a very high degree of safety, and that is because the next section we're going to look at after this is going to be radiography, which uses X-rays or gamma ray sources, which can be fairly dangerous. It also doesn't really use there's no chemicals or anything involved like that, so you don't have that chance of like skin reactions and inhalation, from the vapors like you do for like liquid penetrant or stuff like that. Some of the disadvantages, however, is that it can be affected by infrared radiation sources in the environment, and there are a lot of these. These are just a few examples. But even things like lights, even these LED lights that we have in the classroom, they're going to give off a certain amount of heat. And so that will affect a part and how it works thermographically speaking. If you're trying to inspect things outside, the sun can be problematic, both on the material as well as if you were to accidentally point your camera at the sun, you'll fry your camera because the sun has a lot of infrared energy coming off of it, and it exceeds the ability of your camera to see it. Even things like electrical. If you have exposed electrical wires running, they generate heat. So anything that can generate heat, air ducts, we've got these air ducts around the room. Those would be a heat source, and so that can reflect off the surface and give you false readings. It requires specialized equipment and training, and that equipment can be, at this point, is still fairly pricey. You can get fairly inexpensive cameras, a few $100s, but their resolution isn't that great. It's not even like a standard def. It's only like 300 by 300 or 300 by 200 pixels. So compared to your phone camera, right, visible camera on your phone, that's doing 3,000 by 4,000 pixels, something like that. If we have material that have variabilities in emissivity and infrared reflectivity, which we'll talk about what those are, those can negatively affect results. It's difficult to determine the size, so really this is a good method for finding flaws, but it's not great for measuring. And non-uniform materials can hide indications. Non-uniform materials can show up as some kind of an indication in their own right. So we have to take that into account and keep that in mind as we're performing an inspection. At its basic form, thermography is if we have a properly laminated or bonded material, or something like metal that has uniform kind of thermal characteristics, the heat energy is going to want to conduct and diffuse through that material fairly evenly. So if you have a piece of metal and you start to heat it up, for instance, ultimately that whole piece of metal is going to get to be about the same temperature. But not necessarily right away. It takes time for that energy to move through the object. And what we can do is use a camera that works in the infrared range to monitor or to track that movement of heat through an object. And any kind of discontinuity, so disbonds, delaminations, inclusions, cracks even, can create an anomalous thermal signature. It will essentially block or disrupt the smooth transfer of heat energy. And so you can potentially locate those kind of flaws or those kind of features because that occurs. A few things, couple things here. Heat capacity we'll look at in a minute, but this is it's the measurable quantity equal to the heat added, okay? And then thermal diffusivity is the ability of material to conduct thermal energy or move thermal energy through it as well as to store. So there's a lot of different applications for this. As I mentioned, things like delaminations and voids and composites, those top two in the left-hand corner there are very common. Also, you can find things like impact damage will cause either layers of composites or layers of material to separate, which creates an impact damage void or delamination. You can see how fibers run through. So a finished material, if you need to know fiber orientation, say you're doing a repair and you're trying to match up the fiber clocking and the fiber orientations, you can use it to sometimes figure that out. Glue and various materials, glue is going to change. Water ingress is a big one for aviation. So the second row, third from the left. Water ingress is composite materials are prone to absorbing water over time, which makes them heavier. It can also throw balance of things like flight controls out of balance. We can look at different spot welds, metal, corrosion, contamination. And the one on the bottom right there is fluid level. These are often used in food processing plants where, say, you're filling like cans of Coke. And you want to verify that the fluid is the pop or whatever you're filling your vessels with. If it's something you can't see, you want to verify that you're filling them correctly. So, things like fluid levels and that kind of thing. So some of the terminology we have to understand, there's some general terminology and then there's terminology that's specific to infrared thermography. So the first one is heat. And what is heat? So heat is the transfer of energy. Okay, we feel heat, that's thermal energy transferring to our body. When you feel heat against your skin, if you go stand in the sun, you feel the heat from the sun. That's the infrared energy from the sun entering your skin. Okay? It's heat in its own right is not a thing per se. It's the transfer of energy. What the thing is infrared energy and the energy contained in the object. And so you get that transfer when there's a difference in temperature, a difference in the amount of energy, the average kinetic energy of the molecules in an object or a system. So the more energy the molecules have, the more they're bouncing around and moving, the warmer, the greater the temperature of an object. And if you have an area that's cold and an area that's warm, or an area with low energy and an area with high energy, that energy is going to want to move from the areas where there's high energy to the areas where there's low energy until everything's balanced. Okay, it wants to get into a state of what's called equilibrium. And so we can track that by looking at the heat that it gives off, as that an object gives off. When we're doing this, one of the things we have to do is calibrate our equipment. Equipment is calibrated using something called a black body. And a black body is a perfect absorber and emitter of radiation. We'll get into what emitter is in a second, but an absorber is, we've all probably experienced different surfaces outside especially. Some things heat up a lot more than others when they're in the sun. You walk on concrete, white concrete, it's fairly cool. Then you step onto blacktop and you burn the bottom of your feet. Or you step onto a metal grate and it's even hotter still. Growing up sailing, it was who could stand on the metal manhole cover the longest. But at the sailing area. But a black body ideally is going to absorb all infrared energy that comes in contact with it. Now, there's no such thing as a true perfect black body. And we'll look at what happens there in a second. So some of those properties, emissivity is probably the most important for infrared thermography. And emissivity is the ratio. Like I said, nothing is going to perfectly absorb infrared energy. Some of it's going to be reflected, some of it's going to be conducted. And we'll look at how that is in a diagram in a minute. But emissivity is the ratio of the actual amount of electromagnetic radiation emitted, which is the energy that's absorbed and then re-released, compared to an ideal black body at the same temperature. And again, there is no such thing as an ideal perfect black body. That's a theoretical object. There are things that are pretty close. When they calibrate these cameras, they have these boxes that they point the lens into. And they are painted on the inside with a special, extremely high emissivity paint, almost a perfect emitter. And then the box itself is very insulated, and they can set the temperature of the box to a specific temperature and are able to do that. There's no reflected energy or anything like that inside of them. However, it's not perfect. It's like 0.999, it's 99.999% emitter, a 99.999% emitter. Okay. In general, now we can't confuse visible conditions or visible properties with infrared properties, okay? And the example I'll use is glass. If we look through a pane of glass, what do we see? Is glass reflective, or does it allow us to see through it? Allows us to see through. In the visible spectrum, glass is basically clear. It's an almost perfect transmitter of light. However, in the infrared spectrum, glass is an almost perfect reflector. If you point an infrared camera at the glass window here, you won't see through it. What you will see is a reflection of your heat. I'll see the outline of my body, I'll see the lights reflected from the ceiling, but I will not see anything outside the glass. So glass is an almost perfect transmitter of light in the visible spectrum. It's an almost perfect reflector of energy in the infrared spectrum. So typically, things that are dull and black have a very high emissivity. And emissivity runs on a scale of 0 to 1. It's a percentage scale. So glass actually has a very low emissivity. But again, this is dull and black. That's in the visible spectrum. It's not always a perfect correlation. Okay? Reflectivity is the amount of infrared radiation that bounces off of a surface. So that's what I was talking about with the window. The window is an almost perfect transmitter of visible light, but it's an almost perfect reflector of infrared radiation. Okay, so the amount of infrared radiation that bounces off the surface. And emissivity and reflectivity are inverse of one another. So a window that reflects does not absorb and then re-release infrared energy. It purely bounces off the surface. Whereas a near perfectly emissive object, an object where its emissivity is close to 1, the energy gets absorbed into it and then re-released. It's the difference between a reflection and then an absorption and re-release. Thermal conductivity is how well that heat energy transfers through a material, internal heat transfer. Remember, that energy wants to move from areas of high energy to low and create a state of equilibrium where everything has the same energy. And then diffusivity is the rate of heat transfer. So thermal conductivity is the ability to transfer heat. Diffusivity is how fast it's able to move that heat energy. Okay? They're directly related to one another. A more conductive material also has a higher rate of diffusivity. The heat tends to diffuse through it faster. A lower thermal conductivity has a lower rate of diffusivity. So we're looking at the infrared range, and we've seen the spectrum before when we looked at ultraviolet and black lights when we were doing liquid penetrant inspection of magnetic particle. And in that case, we were to the left. We were to the left of the visible range. You can see the visible range there is that very, very small range in the entire electromagnetic spectrum. For infrared, we're going to be looking on the opposite side. We're going to the right, in this case, the longer wavelength energy than the visible light that we see. And so this is in the range from 0.75 nanometers up to 1 millimeter, that red box that I put there. Okay? But that whole range doesn't always work the same. So infrared cameras kind of come in two main types. They can operate in what are called two bands. The first one is called mid-wave, okay? A little bit short, middle length wave, and that's not what I have circled here. The circled part is the long wave. We'll get to in a second. But mid-wave is centers around 3 to 5 micrometers of wavelength, and that is used for gas imaging. We can actually see gases escaping, and one of the groups mentioned doing something like this, and this is what I sent you guys back to say, hey, you know, these are a specialized camera that's used for gas imaging. Kind of a neat thing. They are a higher frequency, shorter wavelength camera. There we go. For thermography, for infrared imaging, we're going to use what's called long wave IR, and that's closer to the right side of the infrared spectrum. And that's 7.5 to 14 micrometer. Okay? And this is what our cameras that we're going to be using here are designed to detect. Our cameras are not designed to detect gas. They're not for gas imaging. You have to have, it actually has a separate, different type of sensor tuned to a different wavelength of energy. So we're in the 7.5 to 14 micrometer range, and we're going to look at that. That is the range where energy is emitted from objects after it's been absorbed. So an object absorbs energy, and then as it gives it off. So what you can experience with this is, you know, you put an object out in the sun, right? And then you bring it into a cool room. That object's still going to feel warm if you touch it. That's energy being emitted from the object once it's moved into a cooler environment. Or you have, like my water bottle that I put ice in this morning. When I grab it, it feels cooler. There's energy being emitted from the room into the bottle. That's absorbing energy. Okay? Once it warms up, it can then re-emit it. So we're going to be looking in this range. So again, that's why there's a difference. You know, what the properties of something in the visible range don't necessarily match the properties of an object in the infrared range, like glass being the big example that I mentioned. So how do we do this? Thermography has, as a process, has 3 basic steps. And that is, the first one is excitation, which is known as stimulation. This can be either heating something up or cooling it down. You can actually perform imaging either direction. Then we have to take temperature measurements as an object its thermal energy is increasing or decreasing. And then we can analyze what we see from there. So each of these then is broken down a little bit as well. The first two, stimulation and analyzing. The measuring pretty much is always done the same way. But stimulation can be broken down into passive or active, and this is kind of a quick chart, and we'll look at these in a little more detail in some slides here. Measuring the surface, that's what we use our infrared camera for. So you can see the camera is only one part of this process. It's not the be-all, end-all. And then analysis can be done either with raw images, just straight looking at the thermal image that's produced, or we can process it and perform analysis on it to kind of get a little bit more detail in what that's used for. So excitation techniques, things can be passive. This can be passive, and these are where you're not actually turning something on or off in order to produce excitation. So common ones you see there are things like solar heating. You move an object out into the sun from the shade, it's going to start to warm up. You move an object from the sun, from a sunny area into the shade or into a cooler room, and it's going to start to cool down. And that's what ambient heating is. You know, you turn on the heaters in the hangar, and the plane starts to warm up. You shut the hangar door, you shut the heaters off, you open the hangar doors on a cold day, the plane starts to cool down. If you're lucky enough to be in an air-conditioned hangar, you open the hangar doors. When it's hot out, the plane starts to heat up. So those are all forms of passive heating. Active is where we specifically kind of turn something on or off or apply heat energy in a specific location. And so these can come in many forms, but common ones are optical, which is typically flash, step, or modulated. You know, LED lights, not really good for this. They don't put off a lot of heat. But older incandescent or halogen type bulbs can put off a fair amount of heat. Right? They put off a lot of infrared energy. That's why they're not as efficient as an LED. An LED wastes a lot, or sorry, those halogen or incandescent bulbs waste a lot of the energy that goes into them as heat rather than light, if what you want to do is produce light. Other ones, direct contact. We heat something up and put it against the surface. We heat up one object that's not what we're inspecting, and we set that against the object we're going to inspect. Forced convection, this is blower type air blowers. And electromagnetic induction is when you've all experienced electromagnetic induction heating so far. Anyone know where you've experienced it? Where do we see this happen? Yeah. When you did magnetic particle inspection, you either put a part into the magnetic field in the coil, or you ran current through a part and it heated up. That's from that changing magnetic field. So electromagnetic induction can be used for this as well. Passive techniques typically are used for qualitative inspections. Okay? This is something there? Do I see something? Checking for the presence of trapped water, checking for the presence of a delamination, checking for the presence of impact damage. Is there ice in the structure? If you get moisture in a composite structure, like a flap or a flight control or even a fuselage on some of the newer aircraft, and then it goes and flies at 40,000 feet where it's negative 40 degrees Celsius, that water is probably going to freeze. Over time, that water freezing will expand and it can actually pop the composite layers apart or soften them. We can also use it to examine or look at underlying structure. What does it look like underneath the outer skin, underneath the layer you can see? Because remember, these techniques can be used for both surface and subsurface investigation, flaws or to look at features. Active excitation techniques tend to be used more for instances where you need where you're trying to find a quantitative information. So things like size, area, depth, or the extent of damage. Okay. So again, you can use qualitative to find delamination, but you may not be able to find the size very well. You just say, yeah, it's there. If you want to actually measure it, then you tend to need a little bit more specific, you need a heat or cool area specifically and image those areas. And a common way to do that is with flash heating systems. Once we've excited, then we're going to use our camera, and here's an example of the camera we have and a result of what you get. We can use our infrared camera. Now this is a metallic structure that's shown here. Okay. And what you get are colors, blues and purples tend to be colder. Okay, this is relatively speaking, these are temperatures relative to each other. Red and white are your warmest areas, and then it kind of goes blue, green, yellow, orange, red, white are your hottest areas. So you can see there's some areas that are warmer or colder. What's that line running from front to back here? What do you think that is? The red line. Kind of makes this grid, right? What's that grid you see? That's the structure. An area where you have a stringer, for instance, or a rib, is going to transfer that heat more directly into the skin than an area that has air behind it. Or that, in fact, most of these places between the ribs and that are going to have insulation in them, right, to prevent the heat from inside the aircraft from transferring out. But an area where you have a metal rib behind the skin or a metal stringer or longeron or whatever you want to call it is going to transfer more heat to the skin. What about this big red blob kind of behind the flight deck windows in front of this door? I have an idea what would be right there. What's that? Some kind of an electrical bay. Yeah, typically you have circuit breaker panels behind the pilot, co-pilot, right behind the crew seats. So remember, electrical equipment generates heat, and so you probably have an avionics rack or something like that behind there. Anyone know why it's really blue right here? Top left corner. That's looking at the sky. When you look out into space, how much thermal energy is there if you're not looking at the sun? There's like none. It's freezing cold, right? It's almost near absolute zero. So if you point, even if I point my camera up at the sky today, nice blue sky day, right? It's going to image the heat that's coming in from that part of the sky. There's not much heat coming in from that part of the sky. It's all coming from the sun, right? So you get those real dark areas behind there. Same thing with the glass. You can see the windows here. This front window is probably reflecting sky. Side windows reflecting sky. Maybe maybe there's a building behind the camera person taking the picture or something like that. And so that's what you're getting off those windows. That's that glass being an almost perfect reflector. Now, if they had the windshield heat on, those would be bright red. But right now that they're cold. Okay. You can see some of the items like the gear doors and stuff like that are hanging down. They're cold, right? They're out in the environment, so they're fairly cool compared to the inside of the plane. So it's probably a somewhat cool day, or cooler than the inside of the plane. The plane is warm inside. Maybe they've been running the environmental control equipment. The electrical stuff is on. Right? So you can tell a lot just from the picture there. So the camera we're using looks like this. This is actually the same type of camera we've got, the FLIR E95. And it's kind of a bottom of the professional range, I would call it. It does about standard definition video, 640, 480 thermal video. That runs about $8,000 to $10,000 to get into that range. If you want like a high def, you can get high def versions of these. They're in the $40,000 to $50,000 range. So the technology is still fairly expensive for the thermal sensors that are there. And then we can analyze it. Then we take those images, and the image, what we're seeing here, these images, are basically a bunch of temperature measurements, hundreds or thousands of temperature measurements, that software in the camera or software on a computer has assigned colors to different ranges. It's not an actual picture of it. It's a representation. We can actually change what's called the color palette for different things. What it is you basically get a big grid of numbers. It's like a spreadsheet. And it tells you the temperature at each pixel. It's like hundreds or thousands of little thermometers. And it tells you the temperature at each pixel. And so there's a couple things we can do. One is we can do raw viewing of that. So now we're getting into the analysis technique. We can directly view the infrared image. We can do some what's called thermal tuning. That's adjusting the different ranges on it, the ranges of the colors. That's adjusting the colors. That's adjusting what we want to actually look at. And we can look at it directly. And like here we can see that on the left here, this can that's kind of in the middle is more full than the can on the right, because liquids tend to absorb more heat. We can also process it. We can have a computer look at those individual pictures, and there's all kinds of different algorithms that can be applied. And basically the computer looks at pixel 1.1 and compares it to pixel 1.2 and compares it to pixel 1.3 and compares it to pixel in the row 2 number 1 and row 2 column 2 and row 2 column 3, right? You have these different software packages that can compare those different and can look for trends in how those temperature measurements are changing as you go across this big grid of pixels of temperatures. And that's what a qualitative analysis can do. Sometimes, running a logarithmic algorithm on there will bring out things that you wouldn't be able to see with the naked eye. Or you can feed that data into a computer to automate the process as well. So thermographic, what's called signal reconstruction, you can lock in certain things, so lock in certain values and then compare everything else to that value. There's principal component analysis, pulse phase, just there's different terms for running these different algorithms on the individual pixels and then comparing them. So again, the qualitative, the raw viewing is good for, is something there or not? And you can do some rudimentary measurement. You can say it's about, that damage is about 1 inch across, if you know how big the pixels are. We'll get into doing the calculations manually here in a couple minutes. But the quantitative, by processing it, we can get more information, more definite, like what is the depth of the damage? What is the thickness of a part? How is the diffusion of heat energy changing over distance? Is it changing linearly? Is it changing logarithmically? Is it changing exponentially? That can tell us information. That's getting into that again, those algorithmic analysis that can bring additional information to the surface. And like I said, it can also be used for automating the process. Where I went when I got trained on this, the facility I went to do training, it was a company that hosted training at their site. Their whole business was automated thermographic systems. They would look at, and it was primarily sealing like food packaging. So after, if you have one of those pouches where it's like sealed together, after it was sealed, they would take a picture of it to figure out if the seal was done correctly, if they were pressed together and actually bonded correctly to make sure there weren't any holes where your food would go stale. Or they could do it they would look at like panels, like plastic panels that got thermally welded together to make sure there weren't any cracks for the automotive industry and things like that. So thermography is different from the other methods that we've looked at so far because it's an indirect process. I guess the other indirect process we've probably studied at this point would have been like borescopes, videoscopes, fiberscopes, where you're just observing. But an indirect process is, in this case, energy is absorbed by the object and lost by the object, which alters its surface temperature, alters how much energy you're able to detect at the surface. And so what's happening is the energy is going in and diffusing through the object. Okay, it's changing the energy contained in each molecule of an object. And that energy is being absorbed into the object, and then it's being re-emitted, and we're measuring it being emitted. Okay, it's not an echo going in and bouncing back out again. Okay? So energy transfer takes place, it diffuses through the part, and then the results change the infrared energy that emanates or that comes off the surface. That's compared to direct processes like radiography, ultrasonic testing, eddy current testing, where the energy that's put in is measured, the same energy that's put in is measured after it passes through. It doesn't actually cause the part, it doesn't actually change the energy in the part necessarily. Right? It doesn't, that energy isn't absorbed, it goes in, it reflects, it comes back out the surface. In the case of like an ultrasonic pulse. And so that's where we get the term, that thermography is indirect versus direct in some of our other methods. The energy from eddy current testing, you have a magnetic field developed by a coil. That magnetic field causes a current to run, which causes other magnetic fields, but it's never actually increasing the energy of the part necessarily. You might get in theory, a little bit of thermal heating when you're doing eddy current testing, because any kind of a magnetic field, right, can cause a change in temperature. But that's not what you're measuring. You're measuring the resultant magnetic field from those eddy currents. So if we look at it as a diagram, we see something like this. So here we have a test object. We have some kind of what's called incident shortwave source, or incident shortwave radiation source. That's some kind of infrared radiation that we're sending to the part. And when that radiation strikes the surface of a material, depending on its reflectivity at its surface, depending on its emissivity, depending on how well energy diffuses through the part, a certain amount of energy is going to be reflected, okay, that we see here. But that's not what we want to measure. That's the energy that bounces off the surface. Okay? So an energy with high reflectivity, low emissivity, you're going to get a lot of reflected infrared energy. That's what glass is. When you take a picture, if I were to take an infrared image of glass right now, you would see my body outline. You would see an outline of me. Like looking in a mirror and seeing your face. In glass, you see your heat reflected back to you. That doesn't give you an accurate temperature of the glass or the object you're testing. What it does tell you is what my body temperature is, which isn't what we want to know. So reflected energy tells us how hot something is bouncing off the surface. It doesn't tell us how much energy is being absorbed or emitted from the object. So it's not important to us. What is important is we got to make sure we minimize it and we take that into account, that we don't accidentally take a temperature from reflected energy and use that when we're trying to figure out the emitted energy of an object. A certain amount of energy is going to be absorbed. It's going to conduct through the part, and it's going to be transmitted on the opposite side. We're not looking at transmission for the most part. There are some cases where you can image that transmitted energy, but typically we have our energy source, infrared energy source, and our imaging system on the same side of the part. You know, they're both on the outside of the fuselage. They're both on the front of the flap that's hanging down. Okay. What we are looking for is that emitted energy, the re-radiated energy. So that energy that's gone in the part, and now the part's heated up. It's warmer than the surrounding atmosphere. And that energy wants to get back to a state where everything's the same temperature, right? It wants to get back to that. So that energy is then going to leave the part. And that's what we're going to be imaging. That's what we're going to do. And so the biggest thing we got to be careful of here is that we don't pick up or don't mistake reflected energy as emitted energy. And again, that has to deal with what are the heat sources. We have to calibrate our camera. One of the first steps we do is we calibrate our camera for the reflected energy in the environment. How much energy is being sent to that before we start to do any kind of heating or cooling. Okay? Here's that contrast with ultrasonic testing. It's the same sound wave you put in that's coming back out. It's not the test object absorbs the sound and then the test object makes sound because it's got a bunch of sound energy in it, right? It's the actual sound wave that goes in, bounces off, and comes back to the transducer. Or it goes in, transfers through, and is picked up by a receiver on the opposite side if we're doing through transmission. In order to detect our discontinuities, the surface temperature is going to be based on the geometry of the part, and the geometry includes what has changed with the geometry when there's some kind of a flaw. And so we have to be aware that there's a limit to our detection and sizing. Now, we'll get into what's called pixel overlap. How many pixels do you need to image a part to say yes, there's a flaw? But what the effect is the higher resolution your camera, the more expensive your camera, the larger the area you can image at one time and be able to detect a flaw. But the shape of the flaw is going to play a role in this as well. So there's what's called the limit of detectability. And that is if we take a diameter of a discontinuity and we divide it by the depth, we want it to be greater than 1. So what I mean by that is if we draw two objects here, and we're going to be imaging these from the top. Okay. And in object 1 on top here, we have a discontinuity that's very narrow, like this. Okay. In object 2, we have, say, a delamination that's very wide. Okay. If we're looking at this object on top from above, it's going to be very, very hard to see this discontinuity because all we're going to pick up is this very, very tiny end here compared to the depth of it. Okay. So in this top one here, the diameter, in that case, we'll call it, let's say it's 1. If we take that width, 2, 3, say its depth is 3, 1 over 3 is less than 1, it's going to be really hard to pick that discontinuity up. Down here, however, if our depth, we'll call our depth here 1, and now we take that width, which is like my pen width, and I go 1, 2, 3, 4, 6, 6 over 1 equals 6, right? Our discontinuity or our limit for detectability were greater than 1. This is going to be easier to pick up. That's what I'm referring to when I say one over the other. Okay. So we need wide area. We're not going to find these cracks like this narrow crack. A narrow crack like this that's shown at the top, maybe that's more for ultrasound, something like angle beam testing. Okay. Maybe it's more appropriate to find that if you're dealing with metal, something like a liquid penetrant or magnetic particle. Okay. But if we have this wide subsurface defect here, we're going to be able to see it fairly easily using thermographic inspection. And so what you get is that crack in our bottom one here, this discontinuity, is going to affect how energy diffuses through the part. And typically that crack is filled with a very small amount of air. How well does air transmit heat? Does air tend to be a transmitter or more of an insulator of heat? Heat energy. It's an insulator. Okay? If air's not moving, it's actually a very, very good insulator. That's why you put saran wrap on your windows. You trap some dead air between the window and your saran wrap, and it creates insulation. That's why double pane windows work. Now they put like an argon, which is an even better insulator than air. But even if you get air in there, it's not the end of the world. Usually air also contains moisture, and then you get foggy windows and that kind of thing. Okay. So what you get is in this diagram here, you get essentially a strip of insulation there. So if I have heat, I really drew this in the wrong color. If I have heat making my way up from below, say we heated this object up and now the heat's working its way back out, you're going to get a spot right here that's probably cooler. It's emitting less heat than the surrounding areas. And so you'll be able to see, you'll get an indication where you can see that flaw. Okay. Here, if I have heat coming up, this top one, you can see really it's not going to block much of the heat, right? So that's why it's going to be hard to find this very narrow discontinuity in the upper one. You're not going to get that contrast here that you'll get in this lower diagram. Let's stop there.